Once again, welcome to chemistry classes by Vijay Kumar Sethi, class 11th chemistry. We will start new unit, that is unit 3, classification of elements and periodicity in properties. In this video, we will discuss about early attempts of classification of elements like Döbereiner triads, Newlands Law of Octaves, Lothar-Meyer's curve, Mendeleev's periodic law and periodic table. Dear student, this is simply revision. All these topics you have discussed in the class 9th. Why do we need to classify elements? In 1800, only 31 elements were known. By 1865, the number of identified elements had more than doubled to 63. At present, 118 elements are known, and it is very difficult to study individually the chemistry of all these elements and their innumerable compounds individually. To ease out this problem, classification of elements is necessary. First attempt to classify the element was made by Döbereiner, and he gave law of triads, and this is also known as Döbereiner's triads. What is the meaning of this triad? Actually, triad means group of 3 elements. He arranged the elements in a group of 3 in the order of increasing atomic masses in such a way that the atomic mass of the middle element is roughly the average of the atomic masses of the other 2 elements. Döbereiner could identify only 3 triads from the elements known at that time. Hence, this system of classification into triads was not found to be useful. These are the triads which were identified by Döbereiner. This is lithium, sodium and potassium, chlorine, bromine and iodine, calcium, strontium and barium. If we compare their atomic masses, see, lithium atomic mass 7, sodium is 23, potassium is 39. Now if we take the average of this 7 and 39, okay, then this will come 23, which is the atomic mass of sodium. In the same way, in this triad, chlorine, bromine and iodine, the atomic mass of chlorine is 35.5 and atomic mass of iodine is 127. If we take the average of these two, okay, add these two and divide by 2, we will get 81.25. This is roughly near to atomic mass of bromine, that is 80. In the same way, another triad, calcium, strontium and barium. If we find out the average of atomic mass of calcium 40 and atomic mass of barium 137, then this will come 88.5, which is nearly equal to atomic mass of strontium, that is 88. Newlands Law of Octaves. Newlands arranged the elements in increasing order of their atomic masses and noted that every 8th element had properties similar to the first element. The relationship was just like every 8th note that resembles the first in octaves of music. In this table, elements are arranged, and in the first row, you can see these are the notes of music: sa, re, ga, ma, pa, da, ni. These are the 7 notes. Again, 8th one, sa. In the same way, this is the lithium, and 8th element from lithium is sodium. Properties of lithium and sodium are same. Is it clear? This is law of octaves. But Newlands law of octaves seem to be true only for elements up to calcium. After calcium, it is not applicable. Next attempt made by Lothar Meyer, and he made some curve. These curves are known as Lothar-Meyer's curve. Lothar-Meyer plotted the physical properties such as atomic volume, melting point and boiling point against atomic weight or mass. Actually, the word atomic mass which we are using nowadays, initially it was used as atomic weight, and obtained a periodically repeated pattern. Now, what is the meaning of this periodically repeated pattern? Elements having similar properties will occupy the same position in the curve. Also notice that The elements occupying the corresponding position of the curve shows similar chemical properties. Now just have a look to this Lothar-Meyer curve between atomic volume and atomic mass. If we observe this curve, we find that alkali metals such as sodium, potassium and rubidium, which have similar properties, occur as peaks of the curve. He didn't mention alkaline earth metals. You see, this is the peak, sodium, potassium, rubidium. Halogen elements like F, Cl, Br, which have similar properties, occur at the rising or the ascending part of the curve. You can see this. This one is the ascending part of the curve and this is fluorine. This is ascending part of the curve. This is chlorine. In the same way, this is bromine. Noble gases such as neon, argon, krypton, which have similar properties, occur just before the alkali elements. This is alkali element sodium and before it, this is noble gas neon. This is alkali metal potassium and before it, this is argon noble gas. The same way, this is alkali metal rubidium and before it, noble gas is krypton. Okay. Mendeleev's periodic law. The properties of the elements are a periodic function of their atomic weights. And actually, at the time of Mendeleev, 63 elements were known. He made 63 cards and on each card he wrote the properties of elements along with its name and formula of its oxide and hydrides. And then he arranged these elements in a one tabular form. Okay. And he observed that Mendeleev arranged elements in horizontal rows and vertical columns of a table in order of their increasing atomic weights in such a way that the elements with similar properties occupied the same vertical column or group. Mendeleev's periodic table contains vertical columns called groups and horizontal rows called series. And at that time, 63 elements were known. Can see this is the Mendeleev periodic table and these are the groups. 8 group are there starting from 1 to 8. Clear? Again you see that is 1 to 7 groups are further subdivided into A and B. That is first A, first B, second A, second B, third A, third B. In the same way, fourth A, fourth B, fifth A, fifth B, sixth A, sixth B, seventh A, seventh B. Okay. And these are the periods 1 to 6 or these are also known as the series. This represents the formula of metal or elemental oxide. Okay, formula of the oxide of element, and this represents the formula of hydride of the element. In these formulas, R represent the element. And some achievements of Mendeleev's periodic table. He ignored the order of atomic weights and placed the elements with similar properties together. For example, iodine, atomic weight is 126.9, was placed in group 7 along with fluorine, chlorine, bromine because of similarities in properties. Now you just find out this iodine in this periodic table. This is the iodine. Atomic mass is 126.9 and this is tellurium. Atomic mass is 127.6. According to this, if he arranged the atomic elements in the increasing order of atomic mass, then iodine should come before this tellurium. But he reverted this order. Why? Because he placed because the properties of iodine is similar with the bromine, chlorine and fluorine. Okay. Another achievements, Mendeleev left some gaps in his periodic table. He proposed that some of the elements were still undiscovered. For example, both gallium and germanium were unknown at the time of Mendeleev. He left the gap under aluminium and a gap under silicon and called these elements eka aluminium and eka silicon. and also described some of their general physical properties. This is one of the advantage of this, most popular advantage of this Mendeleev's periodic table. Okay. When these gallium and germanium were discovered later on, then whatever the properties predicted by Mendeleev and actual properties of gallium and germanium, there are much more similarities between these. Again, another achievement at the Mendeleev time, that is, noble gases were not discovered. But when noble gases were discovered, they could be placed in a new group, that is zero group, without disturbing the existing order. Limitations of Mendeleev's classification. He could not assign a correct position to hydrogen in his table. Actually, hydrogen has similar properties with the alkali metals. At the same time, it also shows the similarity with halogens, fluorine, chlorine and bromine. Due to the similarity with both, what should be the exact position of hydrogen? It could not be predicted by Mendeleev. Another one is there is no separate position for isotopes, as isotopes are the atoms of the same element having different atomic masses. Mendeleev periodic table is based on atomic mass. Then any atom has different atomic mass should be given separate position in the periodic table. Clear? And isotopes are these atoms of the same element have different atomic masses, and these isotopes could not be given position in Mendeleev periodic table. Atomic masses do not increase in a regular manner in going from one element to the next. So it was not possible to predict how many elements could be discovered between two elements. These were the early attempts to classify the elements. In the next video, we will discuss about modern periodic table. Subscribe my channel to get new videos of this chapter. Thank you.